Hello, Professor Park. Hello. Hello.
Hello, Dr. Saha.
How are you?
I'm fine. How about you?
I'm fine.
Oh, long time no see. Okay. Wow.
Okay. Actually, we are expecting a good talk from you, right, today?
Oh, yeah. Okay. Anyway, I will try my best. Yeah.
Okay. Thank you. Thank you.
Okay. Yeah. No problem. Yeah. So.
Yeah. Tell me if you have any questions.
Yeah. So my talk starts at 8 o'clock, right?
Yeah. Yes. 8 p.m.
Okay.
IST.
Oh, okay. IST. Okay.
Okay.
So
this is, I think, is in Vancouver. Is around 10. I'm correct.
No, it's in the morning. It's a 6:15 a.m.
6:15. Yeah. Correct.
Yeah.
2 hours. Okay. 10
Yeah.
hours, I think. Gap. Okay.
Yeah. So do I have to turn on? Okay. Somebody else is here. Yeah. Yeah. Go ahead.
Okay. Hi, Phil. Hello.
Oh, can you hear me?
Yes.
Professor Saha, great to see you.
How are you?
I'm doing well. I want to thank you sincerely for this great opportunity.
Yeah. It's our honor to have
please,
you.
the honor is mine.
Okay. So now, what is the current scenario of US regarding COVID, right?
It's coming down again, but it was high, very high. We had 2 different bumps. It was not a nice thing. So hopefully it'll get better.
Okay, that's great.
Yeah, this disease is, it's a tough thing,
Good evening, all of you present here, and good morning to our very distinguished speakers who are far away from us and yet very close to our hearts, and Dr. Bradford and Dr. Park. I welcome you all to this one-day international level webinar on recent trends in computer science and its applications, being organized by the Department of Computer Science and IQAC, Surendranath Evening College. I am Devopriyo Sanyal. I am the coordinator of the IQAC. And on behalf of our college, I very warmly welcome Dr. Philip G. Bradford, Director of the Computer Science Program at University of Connecticut, USA, and Dr. Andrew Park, Associate Professor in the Department of Computing Science at Thompson Rivers University, Canada. I also welcome all the participants who have come from other colleges to join this program. I welcome our teacher in charge of the college, Dr. Supti Saha, and also all my distinguished and esteemed colleagues of my college. So without much ado, I think we can start the seminar, this webinar, and with our first speaker, Dr. Philip G. Bradford. He's such an accomplished person and his resume runs it's so much that I've just shortened it a bit. Dr. Philip G. Bradford is on the faculty at the University of Connecticut. He's the director of the Computer Science Program at the University of Connecticut. He's a computer scientist with extensive experience in academia and industry. Phil, as he prefers to be called, was a postdoctoral fellow at the Max Planck Institute for Informatics. He earned his PhD at Indiana University, an MS from the University of Kansas, and a BA from Rutgers University. He was on the faculty at Rutgers Business School and the University of Alabama's Engineering School. He worked for BlackRock, Reuters Analytics, founded a startup and worked with a number of early stage firms. He was a principal architect for General Electric. Phil has a deep belief in bringing real research to practice. This is the root of his entrepreneurial perspective. Phil has a handful of best-in-class results. His AirDots number is 2, which means actually that he's a collaborator with the very famous Hungarian mathematician Erdos. And he has given over 70 talks in 99 countries, and he's the author and co-author of over 65 articles. So I hand over the floor to Dr. Philip G. Bradford.
Thank you, Professor Sanyal. You're too kind. That's very nice. I'm going to open up my slides and let's see if I can share my screen properly. Hold on 1 second. Let me see what I do to share my screen here. Here it is. My entire screen. Okay. Okay, so we're going to conclude talking about labeled graphs and inclusion-based points to analysis, which is a big title, but just as we get in there, I want to give some credits. I actually started looking at this work in the mid to early 1990s with a colleague, Venkatesh Chapella, who's now at IIIT Hyderabad. Venkatesh and I were graduate students at Indiana University, and Venkatesh and I worked in different areas, but we collaborated, and working with Venkatesh was just a fantastic thing. In any case, there's some other citations I have here as well, going way back, some of them, and some of them are more recent. But I think this area is a nice area, and there's some very good questions in here. And so in the remainder of this discussion, we'll talk about why points to analysis and what is it. We'll have some examples, and we'll look at some key algorithms and sketch their costs and their complexities. And we'll talk about some next directions, which is kind of exciting. And I think there's some very nice things to do in here, everything from typical algorithm analysis to even causal calculus and things. So here's the big motivation. Unfortunately, these things happen to me and perhaps everybody. Here's just a teeny snippet of some Java code up here on the top. And you can see what we do is we set a reference to a null object, or an object ref to null, and then we try to reference a method off of it to string. And of course, we get an exception. And this is a problem. Now, this exception is a dynamic exception. You get this exception when you run the code, in fact. Not before you run the code. So not through static analysis, but in the runtime package. Similarly, on the bottom here, we have a little snippet of C code. And here we allocate some memory to P. And then what we do is we put 50 in that memory location that's been allocated. And then we free it. And then, of course, we assign a new value to it, 99, to this memory cell. It was just deallocated, allocated and deallocated. Of course, we're going to get a problem here because we're trying to put something into a piece of memory that was deallocated. Now, both of these errors happen when the code is running, and that brings up the question: what would it take to do some analysis to prevent this? Now, it turns out that preventing this fully is an undecidable problem, and we'll talk about why, or at least at a very high level, and then we'll see what the consequences of that are. And so, points to analysis, we're going to try to figure out, like on the top case with that piece of Java, does that reference point to something that's not null or something that's legitimate and it has a method called toString? In the bottom case, we might say, does that pointer point to a piece of memory we can still insert a value into? And there's many other things we can do with points to analysis. If we just have an editor and we want to change, or an IDE, and we want to change a integer to a short to save some memory space, just doing that globally may cause harm and may in fact lead to a core dump or a null pointer exception. So there's many other situations that give these type of issues when we don't really know what we're pointing to, or we don't have a clear picture, the computer doesn't have a clear picture. So we often rely on this to be determined during runtime. And of course, during runtime can be dangerous. I mean, we're getting into an age of robots and airplanes being flown by computers and a whole bunch of other things. So getting these exceptions at runtime is not always ideal. And of course, we can trap these errors and we can try and catch them, but that's also adds infrastructure. So in general, this is a pretty hard problem to figure out what variables point to what pieces of the heap. Now, it turns out in some languages like C or C++, you can actually have pointers to pieces of the call stack. And even in some languages like Scheme Lisp and things like this, you can also manipulate the call stack a bit and potentially even modify it. So I'm not even going to worry about that. But if we had a process here, the process would have one heap, may share a bunch of network connections or other things, so it shares some things. It shares a body of code, although each thread may run through that body of code in a different way. And each thread does have its own call stack. And so each thread might go through, thread one might go through the code in one direction, and thread two might have slightly different values and go through the code a slightly different way, and therefore have different call stacks. But they do share this heap, which is where most of our thinking about points to analysis occurs. Because if you look at our examples here, the objects are allocated on a heap in Java. Here we're asking for some mallocating for some memory in C++ or C or C++. That's put on the heap. And so this is just a very complicated problem because all these threads, all these K threads can access that heap. So we're not even going to worry about this complicated model. We're going to go to a slightly simpler model, and we'll talk about that in a moment. Turns out the simpler model is also challenging. Okay, so here's some things. And again, getting an error at runtime is difficult. We can have some tries and some catches and some ways to trap these errors, but that adds risk and adds other infrastructure and gets things bigger, although it's quite effective. So some static analysis that we'd like to look at to deal with these things. One of them is called alias analysis. And that is to say, here's several names. Are these names really representing or referencing the same heap location, or the same chunk of dynamically allocated memory? We also can have a points to analysis. And so what is the set of things a particular variable is allowed to point to or can point to? And this is alias analysis and static analysis or static analysis, alias analysis and points to analysis can be static or dynamic. Or I'm interested in the static part, and the static part's challenging enough, it turns out. Now, again, there are people who intermix these meanings, and that's okay too. And in general, we can just talk about pointer analysis. There would be alias analysis and points to analysis, and these are very closely allied things. But our focus is to look at a piece of code, or have a machine or a piece of software look at code, maybe the compiler or a filter of some sort, a lint type filter. Okay, and there's two real things to talk about, and the literature kind of built out this way. There's intra-procedural, which is a single procedure, intra or inside the procedure. So that's a single procedure, points to analysis. And of course, there's inter-procedural, which is calling between procedures, which, as always, that's much more complex. But in general, we may have may analysis and even may points to analysis, or may aliasing. So aliasing during some program run, so these two variables may in fact be the same memory location sometimes. Must analysis is during all program execution, these two things must be the same. So must analysis actually turns out to be a little bit harder. And we're just going to focus on intra-procedural. That is to say, a single procedure. So we'll have a dynamic heap, we'll have some other program space and some other resources, potentially some sockets or whatever, and we have a call stack. And again, we don't even need the network stuff. We're going to kind of ignore that, but it's all really good. So here's a C-style language, and we might have a variable x we initialize to 1. Here we're taking the address, p equals the address of x. Now, of course, x here I presume would be an integer type or something like this, and p has the address of an integer type. But now p may be able to have the address of a double or a floating point type as well. And so there may be some issues there. What exactly does P point to? And in some languages that are C-style languages, or that are close to the machine, very often we can do typecasting and things like this. And of course, that's great, but it also makes some difficulties in terms of what are we exactly pointing to? Are we pointing to a double, or are we pointing to an int? Maybe X was earlier declared as a double, so this is just going to be a double, and P is going to point to that. And then, of course, we're adding Y to X plus 1, and then we're printing what's pointed to by P. So we can do all these indirections. And so this, as you may know, is an address operator. It gets the address of this variable. This says if P is a pointer to a piece of memory, it says get me what that pointer points to. Now, one of the challenges, we can have pointers to pointers to pointers, and we have to dereference them or put a star for each level to get down to the thing we actually want. And that is one of the challenges in aliasing or points to analysis. Zhang has a very nice paper where he gives a very simple grammar to discuss this. So he says you have an identifier, and this identifier would be a variable name, or maybe a struct name, or an object instance name. Or you can have a star with another expression, and the star is the indirection operator. That is to say, we go get whatever's in this piece of memory. And that could be a value, like here's E1. If it just contains an address, that address may point to a piece of memory right here. And this happens to contain star E1 happens to contain 50. Sometimes we would have an address that points to another address, and then we have to go star to get what's in that other address. And so these things can get complicated. Perhaps that's not the best way to program, but in reality, many cases now when we program, we have to include lots of libraries and other folks' codes. And sometimes that double indirection may, in fact, be very useful. And as we discussed earlier, this is just the address operator. So this is how we start getting addresses. And we have an expression that either is the address of an identifier or another expression. And so just with this simple grammar here of how our expressions work, we just have these two extra operators, the indirection operator and the address operator. It turns out things get very, very sophisticated and complex. So how hard can pointer analysis be? I mean, I have a piece of code, I've got some variables, they've got specific types. And so we're going to assume we have a language that has loops, it has if and else's, or the equivalent of else's. We have dynamic storage, and the two examples we saw in the beginning, we allocated a object instance, okay? And the second one, we used malloc to allocate a piece of dynamic memory. So we need dynamic memory, and we need recursive data structures sometimes. So we have data structures that actually have pointers or references to other data structures. And we can, again, go through and get to those final values we're looking for by using the indirection operator. So there's a famous result in computability theory you may be familiar with. And this result says, if you give me a program to decide if a particular block of code in that program will ever be executed given an arbitrary input, is actually undecidable. Okay, so that is to say, a computer can't always determine without actually running the code to completion. So without running the code to completion, and of course, running a piece of code to completion may take days or weeks or months or years. So we don't really know if a particular block of code will ever be executed. And this is kind of a famous result going back to the halting problem of Alan Turing. Much more recently, in the early 90s, William Landy showed that intra-procedural, that is a single procedure, okay, may alias determination is undecidable. And even more so, intra-procedural must aliasing is undecidable. So I just want to talk about that for a second. So may aliasing says these two variables may refer to the same location in our heap at some point. Okay, and must aliasing says they do always refer to the same memory in the heap, and both of these are surprisingly undecidable. There are, that means that we can't always guarantee we'll ever determine these two questions. And aliasing again is very related to points to analysis. We're going to slide back a little bit to points to analysis in a second. And so here, there's some early work in points to analysis. So this was around 1994. Steensgaard used a union find approach. And what we mean by that is if we had sets representing the points to. So what a points to set is, it says, if I have a variable, does it point to a double? Or does it point to an integer? Or does it point to a structure in memory or an object instance? And that object instance, when we have object-oriented languages, it can get fairly sophisticated. We can have the idea that one object can point, or a subclass of object can point to its superclass. And that's a very useful thing in polymorphism. When we have object-oriented languages like Java or C#. However, that leads to complications of when we want to say, does this pointer to this object have a method named toString? It may, or it may not. And if it doesn't, we may end up in a problem, and we may end up with an exception and a halt of our program. So what Steensgaard's idea, which is a nice idea, is if you have two sets, X and Y would contain the possible types that two variables, X and Y, can refer to. So if we have a left-hand side equals a right-hand side, that is, we take the right-hand side, we evaluate it as usual in our programming language. Once we evaluate the right-hand side, we bind it to the left-hand side. So Steensgaard said, look, we find all of these statements in your code, and this is a single piece of code, not intra-procedural, it's intra-procedural. So it's inside one single piece of code, maybe a big piece of code. If you look at some of the literature, these people analyze libraries of these things and other stuff, which is pretty neat. Anyway, so what they do is they take the left-hand side variable and the right-hand side, if it's a single variable, or boil down, find the variables there for each right-hand side variable. And we merge them. And what merging them does, it says, hey, if these two have the same set that they can be point to, then we're done. If they don't have the same set of values they point to, then we take their union and then we merge the points to of each in X and Y. So we union them, and then we're going to merge whatever, recursively, whatever X and Y point to, and we just continue cycling through here. So we basically build a set. So here's an example of Steensgaard. It's a nice thing. So we have we might scan the code and say, well, there's really three variables in this piece of code. There's X, there's Y, and there's Z. We're going to start out by saying the points to set for X is going to be empty set. The points, before we start the code, the points to set for Y is the empty set as well. And the points to set for Z is the empty set. Then we're going to start our code. And as soon as we say X takes a value of 10, we're going to say, well, points to, X can point to, I put here a Z star. This is an integer in our particular machine representation. So, for example, maybe a 32-bit integer, maybe a 64-bit integer, whatever our machine handles. So X, because where X is being assigned is 10, then it could be really any integer that can be represented on this machine within the constraints of the type of X is, whether it's a short or an int or a long. Now we say, okay, y is assigned whatever value is in x. So that means the points 2 of y is the points 2 of x. Whatever x was assigned is now being assigned to y by transitivity. Plus, if y already pointed to some other things, then we still want y to not to lose those capabilities, but to in fact include them in the new updated points 2 of y. In this case, of this simple piece of code with 3 lines, all we're going to have is simply y is the point 2. Points to y was empty, and then points to x now is updated to be the set of all integers given the particular architecture. So we're just going to have that same set here. Now, here we have z is the address of y, and that's a little trickier. We denote this by saying the address of y is the set that contains y. So that's kind of like an address. The set that contains y is an address of y in a nice sense. And so this, of course, we're not going to limit what z points to. It may have pointed to other things before. So y is an integer in this case, presumably, or some form of integer. But maybe z is just a generic memory pointer that could just as happily point to a double or a float or a struct. But so in case we're going to union z in here, now in this case, z wasn't used yet, so we're simply going to have the points 2 of y, what y can point to, which means we're going to have the address of any integer that can be represented here. And so the beauty here of Stensgaard algorithm is running through all left-hand and right-hand sides, breaking the right-hand sides into their variable components, merging them to see what happened, what percent, these are the merges right here, what things can point to. It really does well. In fact, this is what we call the union find algorithm you may be familiar with, which is a famous algorithm, and it's almost linear time, so it's quite fast, okay? However, there's a weakness in it. And so if we have a Java or object-oriented language, again, we start out with the points 2's all being empty. Then we're going to say, let's take x and give it a value of 10. So now x can point to any integer represented in our architecture. Now we have an object y that is some sort of a new int object. And this object y, of course, is going to be able to point to anything that is on our heap as well as an integer, which is because x, in fact, was an integer, and maybe I should say points to int x, or even points to new of x. So we're going to end up with this giant thing immediately that is the heap address. So the heap address is any address, and we don't really get any levels of indirection or anything else. So what happens here, and then if we say int z equals y, even again later, maybe there'll be a typecast here or something else, but we still end up with this giant heap address. Now we can do some things to forestall that, and Stensgaard's a really smart person, so he had some good stuff going there to maybe we could be careful to look at, hey, this is going to be a downcast, maybe we shouldn't fully do a union, and there's some other things. But in its simplest form, we just keep unioning things, and very quickly they may end up being all heap addresses possible, which is okay. Then Anderson had this other idea that maybe we maintain a subset constraint as we go. And so this subset constraint, and the way people are writing it now is very nice. So we might say x is assigned to y. This is Anderson's points to idea. So he says that simply means x contains at least all the things that y contains. And x may contain more things. If this is actually an object assignment, x may be a subclass of y, and x may point to y as one superclass, it may point to z as another superclass, and q as a different superclass. So x may have a lot of flexibility, and it is, of course, therefore a superset of y, and we just want to keep that thing here. So we could say whatever y points to is a subset of whatever x points to. It may be equal. It might be equal. Maybe x is exactly an integer, and y is an integer, and we're done. Maybe not. Then we say, so Anderson's idea was, now we're going to say P is the address of x. So presuming whatever x is, we're going to get the address. So P actually is at least as big as the container of x. So we'll call that the container of x, or the address of x. So the location order of x is actually in the points to of P. And so P can point to anything where x can be located, presumably on the heap. In some languages, like in C, we could actually push something on the stack, which is a little unnerving sometimes, but that's the way life is. And here, we're going to say Q equals whatever P points to. So Q is going to be a superset of whatever P can point to. So if P can point to integers, if it's defined as an integer pointer, well, then Q can point to that. Now, Q might be able to point to other things too, of course. And so Anderson has a very nice idea. So for all things, all W that P can points to, such that is such that the W, whatever W could be, or is, whatever W could point to is a subset of whatever Q could point to. Okay, and so W, for example, gets to the issue of pointers to pointers to pointers. So if actually P could point to another pointer, so we'd have to take two levels of indirection to get the actual value that eventually goes there. We could do that by figuring out, well, whatever P may just point to an arbitrary address, and then the pointer that P points to in that address may only point to doubles, okay? In which case that this subsetting makes some sense here. And similarly, here we have the exact same thing. Let's see, so here R is here we're saying whatever R points to, we're going to push P into that location. So here we have star R is a superset of P, is whatever R, whatever P is, we need to push it into or whatever R points to. P could be an address, P could be, in this case it is an address, but P could be other things, could be an address of an address, and all those other good things. And so in this case, we have a similar thing going on here in terms of the W that, so here we have for all W that R can point to, or points to, are so that whatever P points to must be a subset of whatever W points to. So this again is trying to handle the important but risky idea, and maybe very useful idea, to be honest, of having a pointer to a pointer to a pointer to a pointer. And there's many algorithms that use things like this. For example, pointer jumping. If you want to go through a linked list, and you can do pointer jumping, so you have pointers to pointers. And these are very effective and useful algorithms. Of course, they do add to some complexity depending on if that pointer jumper is jumping through object instances or things like that, then we might have something interesting. Okay. And so in Anderson's idea, so here is again a series of instructions. P is the address of A, so P actually contains addresses of A and maybe more. Q equals P, so Q is at least bigger than P, and this is really mimicking how programming languages kind of work in their when they do their typecasting. So here P is the address of B, and it's another, so P is a superset of B. But now I'm going to go over here. So P points to really has been updated. Okay, so here first points to P is going to simply be A, or whatever A points to, I should say. So maybe I should put parentheses in there. Then P over here is going to point to whatever B points to, so I should probably have had some friends here. Then Q, contains P, so Q would be point to whatever A and B point to. Initially, Q, before this whole thing starts, Q points to nothing if Q is a pointer. R, if R is a pointer, R will point to nothing initially, and then it will point to whatever A or B points to. And then A and B never point to anything because we don't know what's in them yet in this list of code here. So we can build up our points to that way. And so one of the ways that Anderson works on this is through transitive closure. So what that means to say is if we have an assignment x equals y, then as we said before, that means whatever x points to is at least as much as what y points to. X may point to more things, but what this means is we're going to say, well, y points to x in our graph. Okay, so as to say, whatever y can point to, x can point to that. Maybe x can point to other things that'll point to x as well. So x may get other arrows coming in. If x holds an address, y may be an address to a double. Another address might be to an integer. Another address might be to a certain object instance. Okay, and we're going to start with a graph where each variable is a node. Anytime we just have strict equality, which means this points relationship, we're going to have a relationship saying you can get to x by an integer pointer, maybe you can get to x by a double pointer, you can get x by a pointer to an object instance. And then the question becomes, if I get to x through z, so if I have a z that goes to y, then therefore the z also goes to x. So we can do transitive closure to map these things as much as possible. This is a transitive closure algorithm. I don't want to dwell on this one too much, but this basic transitive closure algorithm, we start with all of the nodes, and we pull out an arbitrary node, and we figure out whatever it points to, and then we see how we can extend it. extend things going to it and extend things coming from it. Okay, so we try to extend X, whatever goes to it and whatever goes from it. And this is transitive closure. And here's where we actually rebuild or extend our points to elements here, and we end up with a graph of some form. And this graph, a little bit different this is Anderson's graph, a little different from Steinsgaard's graph, in that we're going to have edges here. Okay, and here's for example, P gives the address of A, so P points to A. Okay, and then Q points to B, so Q points to B, the address of B, and P still points to A in our code as we march through our code down here. And then star P equals Q. So star P says whatever P points to. Okay, well P, if we go back here, P points to A. Okay, but Q points to B, the address of B. So we're going to actually say, so whatever P pointed to, so A is going to whatever. So this is going to be A is going to actually point to B because P pointed to A. Okay, up here, and whatever P points to, which is A, is going to now point to whatever Q pointed to, which is B. So we end up with these two pathways to get to B. And this is going to be useful information in static analysis. Okay, and this is the basic idea. But now, of course, we might also say now, of course, P can go to B and then right through A. But just having that graph there and knowing where we can get to and when we can get to it is very useful information, even with a static analysis. It's extremely nice. Then I'm going to kind of change the game a little bit, and I'm going to pull up a teeny piece of code. And so this is a natural extension of the points to analysis. And here we have a object instance A that has a field. I just called it field. And what we do here in some function f, now here we're having multiple functions. So now I'm changing from intra-procedural to inter-procedural things. And inter-procedural things have an extension, and this is where my friend Venkatesh showed me some neat problems. When we have a function and we call it, and then we execute it and we're done, that's like opening a parentheses for the initial call. We execute all the things inside it, then we close the parentheses when we return. Okay, but before we even get there, I want to talk about this field here. And some folks in the last about year have been talking about this. Well, when I first assign this field to something, okay, that might be like closing a parentheses because I have somehow a.field has gotten a value. I'm putting it into Z. Then here's my a.field, and then I may update a.field, and I'm going to close this parentheses here. So these matching parentheses, this close here, this open parentheses says a.field is being used. Okay, boom, we push it out here. It's done. Then we go to a.field, and then we're going to update it. And once we update it, we're going to close that. So the use updating operations will be surrounded by parentheses. Okay. And then, of course, we also can have the case where we might actually call a function in between. So here, we're going to say, okay, I'm going to use copy of a field. Maybe I should say G calls a field. Okay, and then that's put into Z. Then we call G of a field. So we go and we call G, we open a parentheses. Maybe I should swap these two. But we open a parentheses, and then we call it. We may do some operation. I feel it may even be passed by reference or something like that. And then we're done. We close the parentheses, and we go back to G, and then we may even modify it. And so these type of parentheses are use and modification. These type of parentheses with sub G are execution through a function. Now, G might be passed by reference, or it might be passed by value. So if it's passed by value, we could still have these parentheses are just denoting that we're actually making a call. That we may not be changing a field, but the fact that we have these here, we might note that they're there. And so this is what inspired me a while back. And this is actually how I met Professor Saha. I met Himadri. I was presenting papers on talks on this topic. And so the idea is, can I now analyze a piece of code as a bunch of nodes with labeled edges? And so I was able to take some very nice work of Alon Galil Margalit based on Yuval. And what I was really able to do is I was able to say, look, if I took a graph that represented a piece of code, okay, a call graph, so how the code was updating variables or calling subfunctions. And every time I would want to put an open parentheses, I would have a +1. I would have a closed parentheses, I would put a -1. So if I got a proper match, I would have a 0, okay? And I'm looking for 0 paths that will tell me that what type of state I'm in. I completely done all the function calls I need on this particular path, or I've done all my use and updates of this variable, so I'm done with this variable. You can, it's free on the stack now. It's got no state that's dependent. Therefore, there's no alias that I'm worried about. I don't have to worry about alias or points to because I updated it, I used it, I updated it. It's not in play at the moment. Okay, and so AG, Alain Gilles, Margaret, and Yuval had this interesting idea that if I, and these are actually exponents, but they would say, okay, there's two values here, so they had 3. N is the number of vertices in our graph. And the reason we do this is so that when we use this as an exponent, really, is to deal with the idea that we can never get a path of more than n plus 1 times 3, because n plus 1, in the worst case, could just be actually, I guess maybe I overdid it here, but n plus 1 could be at most just n of these straight in a linear line. So, and the 3 gives a little bit of a boost, I suppose. And so the key here is that when we multiply this times this, we end up with a 1, which is the 0 case. So if we can search through our matrix product, we can do a matrix product and we can search through and find all the ones, we know where there's local parentheses like this. That is just a pair right next to each other. Okay. And in fact, we can label our edges this way and we can do exponentiation. I'm not going to go there. We have to be a little bit careful of our exponentiation and we have to chase some details. But what that enables us to do is the following. Let's suppose we have a path like this. So we have our plus ones here. This could be we access a variable, we access another variable, we access a third, we access a fourth. We match this variable here, the local one, we match that one. Or this could be function calls. F calls G, calls H, calls I. Then I is done. G is let's do this backwards. So F, G, H, I, H, G, F. Okay, so we go backwards and forwards. We want to make sure that those paths make sense. And so what we do is in the matrix multiplication, one matrix multiply, so the minimum path distance multiply. We're going to add this edge here as a +2. We're going to add this edge here as a +2. We're also going to add an edge down here, this +2. And this is also just very similar to Anderson's algorithm in a way, because this is somewhat like transitive closure. That is to say, hey, I've got 2 +1s. I might as well combine them to a +2. To get to here, I can go by +2. To get to here, I can go by +2, just by skipping this node. But to go to here, though, from this node right here to this node here, I add 1 and I subtract 1, which gives me 0. And that's this green one right here. This 0 means we have a match. We've taken a variable that we're aliasing and we've said, okay, that aliasing variable is not going to be used right now. Its variable was used, it was assigned something. Now it's neutral at the moment. Or we've done with this function call. This function call matches. And then so once we have all these, what we're going to do is we're going to drop all the +1s for the moment and all the -1s. And we have a graph that looks like this. And the beauty here, though, is we have this 0 in here. And so the 0 here, normalizing, I'm just going to drop these simple +1s and I convert these 2s to +1s. So we kind of start over again. No reason to grow these things. Then what we do is we, again, try to do a merger. In this merger, we're just going to look out for zeros. So this +1 plus 0 is going to give me a +1 all the way over here. Okay, that's this +1. This one here is 0 plus this -1. And give me a -1, a long -1 over here. And we still have this 0 going. Okay, and that is going to be important. And so we can extend things. And then what we're going to do in the process also is we're going to join this and this, give it +2, this and this, and give it -2. And we end up with a graph that looks like this. It turns out that we have more than a couple of zeros here. And then, of course, we're going to say +2, -2. If we join them, we're going to normalize those, make them +1, -1. We don't want the numbers to grow too big. Once we do this, of course, now we're going to join +1, -1 in the same sort of way with a matrix multiplication, or you might look at it as a transitive closure, and we're going to get a 0 distance from here to here. And so what we're finding here is we're going to find all the matches, and the matches of the parentheses are all the 0 length green edges, and there's one more here from this big jump here. What that's doing is that's telling us where things match, or where these different variables are no longer being used and updated, or potentially where function calls are executed and undone. So we have this important technology to do this. And before we hit the conclusion, I actually have some code that does this. I want to see if I can pull the code up just for a second here. Oops, let me see our code. So here is some Java code, and this edge here, this here is an edge with a +1 on it. This is the +1 here, and this is a +1, and we have a whole bunch of edges all the way up to n-1/2. So n is always going to be n is going to be odd, I suppose. And then we have a bunch of minus edges, okay, and all these minus edges. So we have exactly what we were just looking at, okay. So we're just looking at this case here. We have a bunch of pluses and a bunch of minuses. And so I built this library, and I'm rebuilding it for a more modern version of Java, actually. And so what this is going to do, I'm just going to run this, and this will tell us that it works, which is maybe not the most profound thing, but it is somewhat interesting. Yeah, let me see if I can figure out how to do that here. Okay, here we go. And so this is one of my unit tests. And one of the important things, so I ended up using so what this is doing is we're actually exponentiating the values that we have. I'm representing +1 and -1 as these values, but I actually exponentiate them and raise one to the other, so they multiply. And in doing so, what that gives us, and I have to normalize so these things don't grow too big, is that gives us a nice algorithm that can do this. But my algorithm avoids Boolean matrix multiplication. That is, I'm using representation. So here's an important thing. Some results just came out this year saying you can't find all matched parentheses on an arbitrary edge-labeled graph. You can't find them all if you use algebraic Boolean matrix multiplication. Well, I'm not. I'm using representation. So I'm not using the typical algebraic model. I'm actually representing these values with these special things. I'm using an exponent here as well. I've not shown. So because of that, I'm able to get this code working. Let me just get this here for a second. Oops, there we go. And I actually was able to do something pretty neat. What I do is I represent my fractions in here, okay, by using let's see what we have here, by using big fractions. So if you're familiar with some Java, we have big int and we have double. And I use big fraction because I have fractions, I'm exponentiating them, and I have the numerator and the denominator, which could theoretically be fairly big, although they never seem to grow too big because I normalize them every time, so they don't really grow too big. But the big fraction gave me some infrastructure that turns to work out very nicely and to allow me to use matrix multiplication of these non-algebraic sets to get there. And in fact, I put this up on my GitHub, and I'm going to start making it available it's already available if anybody has interest, but I will look at taking this algorithms themselves and updating the Java, because I think I use Java 1.7, and it complains a little bit now if you use a more modern Java. But anyway, that is the crux of my talk. So I open the floor to questions, comments, anything folks would like.
Thank you. Thank you very much, Dr. Bradford. And we do have questions. The first question is by Mr. Pinakshi De. His question is, which programming language will be more effective to implement blockchain among Java and Python?
Oh, well, this is good. I've worked with both. Oh gosh, blockchain. Okay, Java. I'm actually, and I may do some of this work with Professor Saha, with Madri. Java or Python. Python for me is certainly easier to work with out of the box. I would say that Java is because Java has some more typing. So Python I like, but Python's dynamic typing can lead to little glitches and issues. Whereas Java's typing is a bit more strict, so it's a little better. But I think right now Python is the way I'm going to see if I can go with some of my subsequent work. I've done a lot of it in blockchain with Java. Java security libraries are good. They're robust. They're big, but they may be too big, so they're heavy. So it's a trade-off as anything else. I personally am moving a lot of my stuff to Python because it's a little bit easier to spin things up.
Thank you, Dr. Bradford. The next question, I think it might be related to the one that you just answered now. It is posed by Shomi Saha. She asked, does blockchain provide the secured way to implement cybersecurity?
I would say overall, no, but it does give a secure consensus-based transactions. Now, a consensus-based transaction means 50% or more agree, right, of a particular transaction occurred, autonomous transaction occurred. If 51% of the people or of the people in the network are hostile towards your interests, it may not be secure. So blockchain helps secure transactions provided they are consensus-based.
Thank you, Dr. Bradford.
Yes.
So move on to the final question, which has been posed by Dr. Himadrinath Saha. So he asks whether we can implement this by using Python. And there's a second question. What is the future research direction?
Excellent question. So I'm actually doing some blockchain, and perhaps with Professor Saha, but in this area of static analysis, one thing that would be nice, but it's an undecidable problem, is when I put up a piece of code. So let me talk about this, and we'll talk about blockchain as well. So this is also useful for blockchain. But when I have a piece of code, like you can see on my screen, I can run this in Java. I actually had run it in my Java, my Eclipse, and it gives you an exception. But this is so simple that a static analysis could actually potentially help. And I'm curious, and likewise here, this is so simple, this will crash too. Put this in your C compiler or G++, and it'll crash. And the question is, can we move from static to a little bit of, can we do a static analysis that says, hey, I noticed that even before you run, that you're going to try to take a reference of a null object. Or before you even run, you freed this thing. Now, of course, it's undecidable to know if we'll ever run a piece of code. So if we have this free as inside another series of classes or another series of functions, we may never be able to tell. So maybe the people maybe this compiler designers are smarter than I am and know that, hey, we'll just stay away from this because there's no way to really tell. But I'm wondering if there's not some decent approximations. They may be very expensive, but if it's static analysis and you just run the compiler for an extra few seconds or a few minutes, wouldn't be too concerned. In terms of blockchain, so that's this area I think is interesting, and the question is, right now, static analysis and dynamic analysis of software, the dynamic work is usually done in the runtime packages. The static is usually done in the interpretation or compilation. I wonder if there's a hybrid in there somewhere. That would be kind of cool to look at. Again, I'm not a compilers expert, but I'm interested in them very much. In blockchain, the areas of research that are interesting, there's a ton of them. And in particular, I'm looking at something that perhaps Himadri and I can work on, and I'll send him some stuff over. But this is going to be about height. So one of the criticisms of blockchains, for example, Ethereum, about every 90 seconds, we expect to get a new node or a new transaction. In Bitcoin, the parent of all these blockchains, or one of the parents, I should say, Bitcoin is about every 10 minutes we expect to get a new node. Well, that's not fast enough for a lot of things we do. If you want to go to a soda machine and get a nice cold water or Coke or something, you don't want to wait 10 minutes, or you don't want to wait 90 seconds necessarily, or if you're doing a financial transaction. So with all of these things, there's a lot of questions now. How can we actually do these transactions much, much faster? Now, there are some people, Buterin has got some work that he's done, and a few other folks have done some work in the blockchain space for high-speed transactions. I want to revisit one of the recent papers on that, perhaps with Madri and his team, because I've been thinking about it and to get there. Now, that could tie into this in a way. These techniques that we're looking at with the points to analysis and things like this, maybe not directly related, but it is always good stuff. And the complexity of the model is quite something.
Thank you so much. Thank you so much, Dr. Bradford. Pinakshi Dev and Sumi Saha, they have thanked you for your very kind replies. And I don't see any more questions here. So we are coming to an end to this interactive session. We'll just end it. And again, I have to say that we are very grateful that you made the time to come to this webinar and you shared something which all of us, all the participants were looking forward to. On behalf of the college, I thank you very deeply, Dr. Bradford.
It's been my pleasure, and it's been a great honor, and I thank you. I thank you as well, Professor Sandel. And
Thank you,
Saha, thank you so much for inviting me. It's sincerely wonderful to do, and I'm so glad that we could do it.
So we might just say that this is one of the good consequences of the Covinar episode, the Corona episode, the virus. It brought
That's right.
together. Yeah.
Yes, sir.
Thank you, sir. Thank you so much.
Thank you.
We shall now move to our second part, in which our speaker is Dr. Andrew Park. A brief introduction of Dr. Andrew Park here. Dr. Park is an associate professor in the Department of Computing Science at Thomson Rivers University. He's a national member of the Institute for Canadian Urban Research Studies, ICURS, and International Cybercrime Research Center, ICCRC, and Senior Research Affiliate at the Canadian Network for Research on Terrorism, Security and Society, TSAS. His research interest includes agent-based modeling and simulation for crowd management, control, and counterterrorism, social network analysis and visualization, the study of people's fear, perception of crime and behavior using virtual environments and computational criminology. So I yield the floor to Dr. Andrew Park.
Okay, thank you very much. Can you hear me okay?
Yeah, it's clear. I think it's clear.
Okay,
I think everybody can hear you, sir. Yeah.
Yeah, okay. So let me see how I can share my presentation. Okay, so can you see my slides?
Yes, sir, it is visible.
Okay, that's great. Okay, so thank you very much for your actual introduction and also your invitation, especially Dr. Saha. So anyway, so today's talk, actually my title is Modeling and Devising Crowd Management Strategies Using Agent-Based Modeling and Simulation. So before I start my talk, actually I was invited by Dr. Saha actually 2 years ago. So I had the chance to visit Kolkata there, and I really enjoyed my time there. So I visited the Victoria Memorial Hall, and I saw everything inside. Yeah, I think this is the statue of Queen Victoria. Also, I was staying at actually a nice hotel, and in my bedroom, there was a lizard. So I had to stay with it for my stay. And another actually a big cultural difference was actually traffic. So I was screaming all the time. Yeah, when I was in the car, where myself was almost hitting all the cars and cows and dogs on the street. But amazing, nothing happened. Yeah, I was safe, and Yeah, that was really amazing. Yeah, it's a very different experience. And I really enjoyed Indian food there. Yeah, I really miss them. Yeah, so someday I might go back there and yeah, enjoy the food and the culture there. So what I'm saying is I can really relate myself to you guys and your place and your culture. So thank you for that. So I'm going to talk about the background of my research program. I have several research projects going on, but I will just focus on this particular one, yeah, crowd control and management. So I'm using this particular technique called agent-based modeling and simulation. So I'm going to explain this and so how I modeled the crowd and police, and how our research team developed the crowd control management system. And I will show probably 3 different case studies showing simulation experiments and their results. Then discussion, and I briefly talk about the future direction of my research. Okay, so I'm sure you have heard about this agent-based modeling and simulation. So there is actually a very famous AI textbook, artificial intelligence textbook, written by Russell and Norvig. That book is based on actually really agents. So I was really fascinated by the agents and how we can use these techniques to solve problems. Yeah, my research is basically a very applied actually research. I really enjoyed Dr. Bradford's actually talk today. Really interesting and very useful. Mine is more application of those techniques and theories and things like that. So here we have an agent. So agent is interacting with the environment. So this agent can sense the environment, and it has really limited capabilities of reasoning, memory, usually short-term, goal-seeking behaviors. But the important thing is that this agent is autonomous. It can make its own decision based on simple rules. So I'm using this ABMS technique to solve many social problems. So in fact, the social systems are very complicated. So just think about, your society, your problems around you related to humans and, the environment around you. There are so many contributing factors and complexity. So it's hard to make, mathematical and statistical models to solve problems. So in that case, this technique ABMS works pretty well. And it can really solve many complex social problems. So some of the benefits of this technique ABMS is that, agents naturally represent the people. As you see, right? Agents can sense and also make a decision, reasoning capability, and, it can remember things and goal-seeking behavior. Yeah, it sounds like a human, right? So we can use agents and they really represent the people. And also another interesting is that each individual has its own fixed rules and capabilities. But when we have multiple agents all together and they behave together, then we can see and observe emergent phenomena that we don't really expect from each individual. So that is really interesting. And it's a very flexible in terms of scaling. we can have just one agent, just 10, 100,000, and so many agents together. And through proper visualization, we can effectively communicate key model information. So actually, I'm a very visual person. I teach computer animation, virtual reality. So, the agents can be just the dots and, it can be very simple shapes, but I love to make them looks like humans so that we can really understand what's going on. There are some limitations of this technique. So we cannot have a perfect a human model using this technique, right? There are so many factors. So we have to extract important factors and characteristics depending on what you want to do, what you want to achieve through these techniques and simulations. But sometimes it's very hard. If you have too little characteristics and factors, then they don't really represent humans and agents well. But if you have too many characteristics and factors, then it's hard to simulate them. And if you have multiple agents, you can easily reach the limitation of the computing power. So you should find the right level of abstraction. So as I said, we can have many agents. Then it can easily reach the limit of computational power. It can be very intensive. So always you have to find the right balance. Okay, so let me talk about my research here. So this particular research program is about crowd management and the control. Some people don't like to use the term crowd control. It sounds like very negative and try to control people. So here, some police officers want to use the term crowd management. It's not really pushing them and force them to do, but we want to help them to be safe and don't let them not to violate any rules and regulations. So first we have to understand what it means by crowd. There are different definitions and characteristics. We have traditional definition, and also we have sports crowds, actually characteristics. And there are recently some new definition and characteristics of crowd. So here, Gustave Le Bon is the pioneer of crowd research. So it was, I think, more than 200 years ago. So I think that you need to really understand the historical background of actually his research. So at that time, there were many, actually riots and some big events against the government, things like that. So he understood the crowd as actually a homogeneous group. So all the individuals share the same ideas and sentiments. So in a crowd, each individual lose his or her personality or even the power of reasoning. Or even we can say they lower their own personality or reasoning capability. And they easily follow a few leading and authoritative individuals. And they are actually easily influenced by actually people's emotions. So some people is very angry just next to you, then you become angry and they just shout and yell at the, government people and things like that. And they take a violent action collectively. So that was actually traditional understanding of a crowd. And actually sports crowd is a kind of special kind of crowd. So they identify themselves emotionally with their team's players. Yeah, they think their team's players are their representatives. Also, they have a partisanship. They are hostile against their opposing team. So some sporting events are dominated by young people and also alcohol. I'm going to talk about the hockey games much more later, but hockey games and soccer games, so many young people get together and drink alcohols, and they are intoxicated, and they can easily become violent, things like that. And when they see their teams losing games, they are frustrated, disappointed, and also influenced by alcohol. They behave disorderly. Sometimes they really become rioters. They also raise riots, and they do some vandalism and become very violent. So, we understand, right? Their teams lose the game and they become angry. But also when their teams also win the games, still they also become violent. They vandalize public properties. They become, even though they celebrate, they become violent too. So that is very interesting. So some research shows that why they become aggressive. The research shows that it is the result of watching a violent and aggressive acts of players, especially, hockey games. Sometimes, the players fight with each other, and that really, causes, the fans become also violent too. So I don't know whether you are European, soccer or football games fans. Football hooliganism is prevalent in Europe, as you know. So they support their own football clubs, and sometimes they have fight against the support of other teams. This is a huge problem. So here we have some new understanding of the crowd. So Granovetter understood the crowd with threshold models. So the crowd has a kind of threshold. If some causes that they go beyond this threshold, then they become kind of radical. They become actually instigators, and they easily join a riot. But at the same time, they are also still rational. It's different from actually Gustave Le Bon. They still have their own reasoning capability. So they think about, okay, should I join a riot, or if I join the riot, then I'll be arrested. So which is better? Which is more beneficial? So still they think about it. But there are different kinds of crowds. Okay, so some crowds have actually low threshold. Others have a high threshold. If you have a high threshold, then you don't really join a riot. So they are called conservatives. They are respectable actually citizens. So here you can see that the crowds are not homogeneous, but heterogeneous. Here, Colin understood the crowd that not all the crowds are violent. Only a small portion of the crowd commits a violence. And most of the crowd, maybe they still support. Yeah, they are still angry, not happy, but they don't really become violent. Just emotionally support. So here again, each individual acts rationally and emotionally in the riot situation. Again, Jagger, the same idea. Understood crowd as actually being heterogeneous, and he thought about 3 different groups. Hardcore, hangers-on, bystanders. So hardcore always joins a riot. Hangers-on, it's between conservative or bystanders and hardcore. Influenced by both groups. They can join or just leave the riot. Bystanders, they never join, only just watch. Here, it's very interesting. It's a new technological era. Baker understood a crowd as actually a mediated crowd. So it's not physically just influenced by nearby people. They can communicate using smartphones or some electronic devices, or through social media like Facebook, Twitter, and YouTube. And so they become a crowd, right? Not necessarily physically, but sometimes virtually. So we can define them as actually a crowd. Okay, so here let's think about police tactics for crowd control and management. So the police doesn't just react to the crowd's behaviors, right? So that is actually a reactive tactic. The crowd does something, then police do something, to stop them and protect them and something like that. But sometimes a police can be very proactive. Okay, before something happens, the police can take an action in advance. So there are 2 different tactics here, but it's important that how the police understands the crowd. If they understand the crowd being homogeneous, then they do something to the whole crowd. Okay. They don't differentiate different groups in the crowd. So maybe this can be very counterproductive. There are some innocent people in the crowd and still they use some force. Then even the innocent people become angry and they maybe just join the riot. But if the police understands the crowd as being heterogeneous, then they do different things, right? Not all the crowds are bad and violent. So they have different tactics here. They can maybe start some dialogue or negotiation. And if it is a lawful protest, the police can actually facilitate, just lead them, protect them. So they can be very effective and productive. So actually, it's hard to find how police manage the crowd. There are a few manuals on the internet. So I found this one, Association of Chief Police Officer, Public Order Standards. So this manual really shows some different police formations. So in the urban environment, the occupying the intersection is very important. So here, the left side, okay, let me just use the pen over here. Yeah, so here we have 3 police lines, right? Here, and here. Some commanders are behind here. So they march towards the intersection to occupy the intersection. And this one is called a 3-sided box. In fact, this is very effective. So they make this kind of box formation and move here. And yeah, so it can occupy the intersection very effectively. Yeah, sometimes they use this wedge formation. So sometimes they have to protect some VIP, yeah, some mayor, or sometimes a president. Then yeah, crowds are here, so they have to make a path so that some VIP can go through the crowd. So sometimes they use this kind of formation. Okay, so based on this literature review, yeah, background study, we began to develop some simulation system. So here we chose 4 kinds of agents. Yeah, instigator, radical, conservative, and guardian. So you already understand. Yeah, I explained how we can distinguish different groups in the crowd. Yeah, instigator, they always join the riot. Threshold is 0, and they really influence people around them. They become leaders, and there are agents called radical. The threshold is not 0, but very low. So they are very easily influenced by the instigators, so that they easily join the riot. And the conservative, these people are, of course, influenced by either instigators or guardians. Their aggression level is not that high. Yeah, but they can join the riot or not, okay, depending on people around them. And finally, we have guardians. They are good people. Yeah, they never join the riot, and the aggression level is always low, and they really influence people around them, especially conservatives. So conservatives are influenced by the guardians, and their aggression level become low. So based on that, we began to develop some simulation model. So you can see here, a red dot is an instigator. So around them, either radicals or conservatives, and guardians are actually the outside, right? Outside, they don't really want to join any riot. And so we developed some different behaviors here. So here we have instigator and either radicals or conservatives can follow this leader. So as I said, I'm very interested in actually visual representation. Yeah, I don't want to use dots. So here we have very realistic human figures that represent agents. So here we have a police model. And also we used a very realistic 3D environment here. So I used a Unity game engine to develop this 3D virtual environment. So we can have different police formations. Yeah, here, all the different. And sometimes we have police on horses. Yeah, so police cars and here. So when the police agents are going through the crowd, these crowd agents avoid these police agents. Yeah. And here we have a police line. and these crowd agents cannot go through this police line. But if they have so many crowd agents all together, especially here we have an instigator, then the police line can be broken and they can go through the police line like this. And also we also added this tear gas. So we can shoot this tear gas and then all the agents run away from this tear gas. So this is the overall structure of our simulation system. So we can have here different police strategy. We can create some different events and scenarios. And we have also environment data. Then we can visualize the whole simulation in 3D. And also we can record the data here. So before I go to the next one, I'd like to ask you, so what is India's favorite sport? Anybody? Okay, so I believe...
Generally, Dr. Park is generally considered to be cricket.
Yes, right, yeah, cricket, right, okay. Yeah, so, I'm in Canada, I'm in the city called the Kamloops, and there is a cricket club in this small city, yeah, organized by some Indian students from my university. Yeah, so, it's very popular. Wherever you guys go, you create cricket clubs, right? So that is nice. How about, what is Canada's favorite sport? Do you know? Okay. Someone says baseball.
Is it ice hockey?
Yes. Okay. Professor Sanyal knows everything. Okay.
No, not at all.
Yeah.
Just
Yes.
guessed it because it's a very cold country.
Yeah, but yeah, right. So ice hockey. Yeah, we are big fan of ice hockey. Even one of my sons actually joined a local ice hockey team. So everybody actually loves ice hockey here. So using our simulation system, we actually simulated this particular event, actually riot. So Vancouver Stanley Cup riot in 2011. So each province has its own hockey team, and we really support our hockey team. So in 2011, yeah, I'm in British Columbia, yeah, province. So we really supported our team, yeah, Vancouver Canucks team, and we could have won the championship, but we lost. We lost the championship to Boston Bruins. Then we became very angry. Yeah, some of the fans became very angry and began to break actually public properties and overturned and set fire on cars. So that's why Vancouver Police Department deployed hundreds of officers to control this angry crowd. Yeah, I can share some of the pictures. Look at this. They were very angry and breaking the cars and overturned and set the fire. And the police had to go and control those angry people. So using our system, we wanted to simulate that. It worked pretty well here, and we did a very simple experiment. It's a very preliminary, yeah. But here we have a police line with 10 police officers, and we had 10 rioters here. They want to break this police line over here. but they couldn't, right? And now we have exactly the same 10 police officers here. Now hundreds of actually angry crowds, and they could easily break the police line. So it was just testing our simulation system here. So we showed this to Staff Sergeant of Bangkok Police Department, who came from the UK and who had 30 years of crowd control experience. He really liked it, and he wanted to use this system to educate new police officers. So since then, we have been working together, and I'm learning so much from him. So it's not just the theory, but how they really do things and manage crowds. So here's the benefits of our simulation system. It's very realistic, and it creates a 3D environment automatically. And we can test different crowd control strategies using this system. And we can also create various scenarios and collect data, and we can analyze the data. Of course, we have limitations at that time. The police model is too simple. So we wanted to improve that. And also, we didn't have real world cases to validate our system. And so that's why I began to work with a police officer who had 30 years of crowd control experience. Then we began to improve our system. So here, Urban Behavior Simulator 2, we simplified the crowd models. So here we have three kinds. Instigator, the same thing. The followers, like either conservatives or radicals. So it can become violent or peaceful. The lawful is like guardians. So we simplified the crowd model. And now we improve the police model here. So we began with a simple police formation, which is a line formation. So this line, police line moves as a group and simply pushing the crowd to disperse them. Okay, so look at this. Wow. So this was the real picture of the crowd for the Stanley Cup actually riot here. It was before the riot, and not everybody joined the riot. So we have a hockey arena, but many people couldn't go into the arena, right? So that's why we have here outdoor big screen, and all the crowds gather here to watch and hockey game and cheer, support their team. So here we had 55,000 people gathered together. Okay. And as you see, there is no space between, people. It's so crowded. So some of the people, right, wanted to leave this place, but they cannot get out of this area because of the crowd are really packed in this area. So in order to disperse the crowd, so here we are doing some experiments. What they have to do is here. So here, so this area is a viewing area. So many crowds here, even outside of this barricade, there are crowds. So in order to disperse this crowd, what the police could do was, they form police line here and here and here, and push the crowd. This way, and this way, and this way. Then there will be some space, and then crowd will begin to move and leave this area. So either we can push upwards, this way, north, or down, downwards, so to the south. So we did some experiments, okay? So if we push the crowd, along this Richard Street, or how about these 2 streets, or 3 streets, then what will happen? And or also the same thing with the going down. If we push them to downwards, then what will happen? And many crowds are using public transportations. We call actually sky trains. If you visit Vancouver, you will know. So we have sky trains, and so those stations are in the north, or the northeast area here. So the crowds actually want to move this way. Okay, so we did a simulation experiments. The result is here. Okay, so this is police line moves away from the Vancouver Public Library, so which is a public library here, and the police lines actually push the crowds this way, upwards here. Okay, that's the case? Okay, sorry. No. Okay, this is towards the public library. Sorry about that. Towards. So first the experiments are actually going down, to the south. Okay, so that is this graph. Okay, so look at here, how long it takes to disperse the crowd. So here about 600 seconds here. After that, what we did was pushing the crowds upwards, to actually the direction of the stations. And it took about 450 seconds to disperse the crowd. So here we understand, right, why there is a difference between these. Pushing the crowd to the north really helps, because that's the direction that the crowd wants to actually go, take. They want to go to the public transportation, right? The sky train stations. So that is a good, actually, strategy, okay? I mean, we can disperse the crowd either, pushing downwards or upwards, but pushing upwards is a better strategy. So we could see that. Okay. So the next study is related to festivals. There are many great festivals in India, right? I searched for it, and there are many famous festivals in India. So what is this festival? I saw something like this at my university too. Is this called a Holi, right? Festival of colors, right? They throw, colored powders. So this is amazing. How about this one? What is this one? I saw this on TV. So this is called Govinda, right? Govinda. So we also have a very famous festival especially in British Columbia, in Vancouver. It is called a celebration of light. So it takes about 1 week, almost at the end of July and early August. And every day we have big celebrations, big music festivals and amazing fireworks, fireworks. And this happens along this beach, So this is called English Bay. And the fireworks actually happen on the sea. So lots of boats and ships, they actually shoot fireworks, and really so many people, come over here. So about 400,000 or 500,000 people every night gather together to watch these fireworks. So it's difficult to manage these crowds, They watch and they want to go back home, and how to help them. So here we have English Bay Beach. Lots of people, come over here to watch the fireworks. And the public transportation, SkyTrain stations are here. So they walk all the way to here and they have to go back. But, okay, so here, so I'm talking about this area here. So here we have many stations, okay? Here, here, and here. So, another station. So they want to go back there. So here we have some simulations. One big issue, I mean, this is really happening. One big issue is this area, okay, this intersection. There is a Starbucks coffee shop. I'm sure you guys have a Starbucks coffee shop, right? In Kolkata. And lots of people just wait here. Yeah, they kind of make an appointment. Okay, after the celebration of fireworks ended, let's meet in front of the Starbucks. So lots of people gather here, okay, here, and they block the road here. So because of this, it slows down the flows of the people. So we have to really solve this problem. So in our simulation, what we did is we blocked this street, okay, this block street. And so these police officers can suggest to people, okay, don't wait here, don't stay here. Okay, you have to go either this way or this way. Okay, usually, we suggest them to follow this road. This road. So whether this might help. So this is the result. Look at here. So this orange color shows no police, no waiting. So let's assume that nobody is waiting in front of the Starbucks coffee shop. Then, the people disperse very quickly, right? The shortest time. And this one, the blue color graph shows that people are waiting and there is no police. Yeah, the police is not blocking the road, no suggestion. Then it takes the longest time. And here, gray color graph shows, people are waiting in front of, try to wait in front of the Starbucks coffee shop, and the police blocking the road and suggest them to leave and follow different route. Yeah, so that is this graph here. So you might wonder why this one, gray color, is not faster than this blue, here, blue graph. The reason is here, okay? So there is no wait, right? No wait. And then people will just follow the shortest path somehow, shortest path to reach the destination. But the police is blocking this street and suggesting to follow the alternative route. So it will be a longer path to reach the destination. So that's why, it takes longer to disperse the people here. Okay, let me tell you. So we showed these results to the police officers, and we had their review. In fact, this is not the real strategy. What they did was this one. The police line was actually positioned diagonally in this intersection. So the people could use this street, okay? But they couldn't wait in front of this coffee shop. So they go this way and they go this way. So that was a very smart strategy, right? Yeah, instead of blocking this one. Otherwise, people wait here. And the interesting phenomena is that when there is no police line blocking here, what happens is that people actually circle around. Okay, circle around it. Yeah, swirling actually movement here, because some people want to go this way, some other people going down here, and some other people take this one. So many people are going here, and they cannot get out of this circle. So they, going around and around. Yeah, there is a swirling over here. So that's why they put the diagonal police line here. So there is no swirling movement, and all the crowds could get out of this area very quickly. So we are going to actually simulate that. Okay. Okay. So as I said, yeah. So we want to have accurate simulations of a Honda celebration of light, and currently we are working on different police formations, how they can effectively disperse people. Yeah, three-sided box, wedge formation, and things like that. And definitely we also want to know, it's not just forcing people, whether we can have different strategies to help and manage the crowd. Okay, so that's the end of my talk today. If you have any questions or comments, please let me know. Yeah, thank you very much. Yeah. So actually, yeah, okay, go ahead. Yeah.
Thank you very much, Dr. Park. It was a stimulating and a fascinating lecture, and it just showed how computational techniques and artificial intelligence, how they can really affect basic aspects of our lives. It's truly wonderful. And thank you very much for that, for those snippets of your memories in Kolkata when you visited us 3 years back. The Victoria Memorial and the food and the auto rickshaw, and of course, the house lizard. We assure you, next time you are coming, there certainly will not be any house lizard there. So there are some questions, Dr. Park, and I'll be giving you the questions. I'll be reading them out to you.
Okay, no problem.
Professor Shukdev Paul from our college, he has asked 2 questions. I'm putting them one after another. One, what is the difference between agent-based simulation and multi-agent system? That's question number 1. Followed by, how is AI embedded in agent-based modeling?
Yeah, they are really wonderful questions. So the first question, agent-based system and multi-agent systems, I believe they are the same thing. Agent system can have both a single agent based system and multi-agent based modeling and simulation system. So depending on what you want to do, you can have just one agent with a very complicated kind of characteristics and so many contributing factors. But if you have a multi-agent based modeling and simulation systems, as I said before, one individual agent cannot be complicated, right? Yeah. Just think about tens of thousands agents running together, and each agent is very complicated. Then you can easily reach the limitations. So depending on what you want to do, you can have either single agent based system or multi agent based system. And the second question, AI. Yeah, I'm having so much fun. Okay, so so in fact, ABMS is directly related to robotics. Yeah, making an agent is like robots. Okay, so robots are like agents, but it's physical ones. But what I'm doing is virtual ones. Yeah, I'm also very interested in robots and robotics. So, AI is essential elements in robotics and these agent-based systems. So, I'm using different AI techniques there. Yeah, we can use machine learning techniques with the agents and the computer vision and all kinds of things. So I hope, I'm answering your questions.
Thank you, Dr. Park. The next question is by Pinakshi Dey. His question is it possible to implement integrating optimization in cybersecurity?
Okay, so cybersecurity. So that is actually my another research field, not directly related to this one. So optimized integration. So it's a big question. So I don't know what that he or she is asking about. But definitely, cybersecurity can employ different techniques, and depending on what you want to do, we can optimize the techniques. And definitely, my answer is yes. So what I did with cybersecurity was that, I was analyzing and visualizing big data. So such as hackers' forum data or some terrorists' forum data, something like that. So we use all the different techniques. So we can analyze sentiment. Sentiment analysis. We have some available software packages to do so. Also, I'm very interested in using visual analytics. So we can somehow visualize this big data in a certain way that humans can easily detect and recognize some patterns and trends. So in fact, currently I've been working on the AIS data. That is actually marine data. So all the ships and boats actually transmit their data to some data center. Those data are available in public. So we use machine learning to detect anomalies, and also we want to detect illegal fishing activities using this data. So it's really fascinating. So the question was really big, and my answer is yes. We can optimize different techniques, and we can apply different AI techniques to analyze the data from cybersecurity and all kinds of big data.
Thank you, Dr. Park. We have a third and final question. It's asked by Surendranath Banerjee. The question is, how can we determine how many techniques the simulation system will generate to handle the crowd? Does this depend on the previous knowledge base?
So the question is how many techniques?
How many techniques the simulation system will generate? How can we determine that? How many techniques will be generated to handle the crowd? How can we determine it? Is it based on previous knowledge base?
Okay. Yes. Definitely. So as I said before, you should be very, very careful. Even though, the computer hardware is becoming more powerful, but my experience is that we can easily reach the limitation, especially if we have multiple agents, hundreds and thousands. So my current simulation system could have up to 5,000 agents. Okay. So it doesn't really reflect the real number of crowds. So that's why we say one agent represents, let's say, 10 real people, something like that. So don't try to use so many different techniques unless they are really necessary. It's important to have just the only necessary techniques and characteristics you have to employ in each agent, so that you can have many, multiple agents in your simulation system. So I hope, I can answer, the question. Yeah.
Okay, thank you, Dr. Park. Thank you so much. The participants whose questions you've just now answered, they also thank you for your very considered and careful replies. So we have come to the end, the real sort of the end phase of our webinar. I wish to thank you again very deeply, Dr. Park and Dr. Bradford. I shall now ask, Dr. Park, do you want to say something?
Oh, no, just I want to say, big thank you for everybody, including Professor Senyal and Dr. Saha. It was my honor and privilege to talk to you today. And also I want to say, I love lizards. I have no problem to have a lizard in my hotel room next time. Yeah, so don't worry about it. Yeah. Okay.
Okay. Thank you, Dr. Park. I'll now ask the head of our institution, the teacher in charge of our college, Dr. Supti Shaharoy, to deliver the vote of thanks.
Good evening. I, on behalf of Surendranath Evening College, like to thank all of you present in the one-day international webinar organized by Department of Computer Science and IQAC of Surendranath Evening College titled Recent Trends in Computer Science and its Application. Today we are very happy to have with us two eminent speakers, namely Dr. Philip G. Bradford from USA and Dr. Andrew Park from Canada. Application of computer is now evident in every aspects of our life. Now, due to pandemic situation, we, the teachers, are unable to take classes physically with the students as we used to do in the classroom. So online classes are only the mode nowadays to reach the students. I convey my heartfelt thanks to both the speakers for their valuable and informative talk on the topic which enriched all of us a lot. In this connection, I like to thank all the faculty members of the Computer Science Department to choose such a topic for the webinar, which is very relevant in the present situation. I like to thank our IQAC coordinator, Sri Devopriya Sharnal, and also Dr. Abhiri Guho and Dr. Himajinath Saha for technical support. I also like to thank all the members of the governing body, all teaching and non-teaching staff of our college for their constant support and cooperation. Without their help, it is not possible to host a webinar like this. I again like to thank all the participants present here who joined the webinar for their cooperation and believe that in future also they extend their hands of cooperation to us like today. So please stay at home, stay safe, and keep social distancing. Let's hope for a better tomorrow. With these words, I like to have an end of today's webinar. Good night to all of you.
you.